It is now 9 o'clock. Good morning. Good morning. TV guy, you're good? Yep. Excellent. Thank you for being back there.
Making sure your moderator was here.
We'll wait till Lena leaves though, because she doesn't get to see this. Yeah, because she's not here. All right. Hello. Good morning. Let's get do a little calisthenics or something for those of you who slept. Coffee. I sell these lovely teas over at the 7-Eleven. So in case you haven't figured it out, most of my talks are excuses to put up pictures of my dogs, who I love. This is what I want you to feel as you're going into the talk. You're peaceful, you're in your happy place. This is a literal picture of my happy place, sitting on the beach with my dog. I mean, you're watching for the cops, because they're not allowed to be there, but you're in your happy place. So yeah, the goal, as I put it on the sucker you guys to get in here, was reading Rust for noobs. We'll see if that's where we went. I had a couple questions beforehand. You've practiced with these. I asked you them yesterday. How many people have used Perl? It's a lot of you, I'm going to guess. Okay. How many of you came to Perl from C like I did? Like a million years ago, but yeah. Or have you used C at all? Awesome. Any like functional languages like ML, SML, NJ, or even a Scheme, Racket, Lisp type stuff? Okay. We got all sorts of perspectives in here. And Rust. Do we have anyone who's used Rust? All right, get out of here. All right. Cool. So, oh, yeah, this is where we're supposed to be for that part of the talk. Right. Hi, I'm Andrew. I'll be your guide today as we look into Rust a little bit. These slides will eventually be up on my blog, Low Level Manager, which it's easier to type spaz rocks. That will take you to my blog. Yeah, so in theory, I'm some sort of polyglot, which means I dabble with languages for a little bit and I get bored. But I started with C and then Perl and Shell. Those were all kind of together. And then Python and ML and Racket and Haskell and Go and Rust all came later. Feel free to tweet along, because again, I promise not to live tweet my own talks. So yeah, we are your tour guides. Here you can also see Gypsy in the other corner. And you can see me because we're in the back seat. So I don't know where we're going either, but my lovely wife is driving. So Rust. Go to Rust right now, you get this beautiful field of text. And I actually finally read it last night. I'm like, oh, this could have been my talk right here. There's a lot of good stuff right here. They've got so much, it's hard to really tell you. It's performance, it's reliability, it's productivity. They're looking at the whole package. They want the language to go fast. They want your experience to be good, both running it and programming it. And I'll actually touch on a lot of what's on there so you don't have to read these little words. And, oh, right, and what is my Rust experience? Because the last time I was between jobs, I spent about 3-4 months playing with Rust, and it was pretty fun, and that was 3.5 years ago. And it was right around the 1.0, it was just before 1.0 came out. And so it was changing a lot. There were a lot of pieces that were missing, but it was still fun. And then my next job was very busy for 3.5 years, and I didn't play with it very much. I tried a couple times, but I didn't have much time. And then last few months, I have been playing with it again. It's 3 years after 1.0, it's 1.3, it's somewhat stabilized on features, and it's been really fun for me. Also, I don't do it for work, so it's really fun for me. It's great. So it's compiled typed language for systems programming. And a lot of the early talks you would see were all about how to do systems programming with it. Rawr! I'm like, I don't really want to do systems programming, but I like a lot of the other things that it gives me. So it has been developed by Mozilla for Servo, their new rendering platform, to make the web, faster and safer in there. Hey, what's the name of their browser there? Firefox. That's right. Who's a big Firefox fan? First hand up. Who was first? You were first? Yeah, that's right. Okay. when I was like, hey, talk to me about Rust, and they're like, you mean like from Firefox? Awesome. It was a great conversation. But they have sort of co-evolved that project in the language, which has given them a big playground. It has changed a lot from like the 8 years it was before 1.0. But you get the power of low-level programming with the feel of a high-level language a lot of the time. And one of the many mottos is safety, speed, and concurrency. You take all three. So they can't add things if it's going to violate one of those, which is really, it's pretty amazing. Also, when I crashed my slides, I also lost the ability to get to the extensive notes I've written. So this is kind of fun for everybody. So I would say some of the core features of the language experience and or the language itself. So one is the one that's kind of scary for us. It is a static type system. On the bright side is a static type system with local type inference, which means if you've come from, say, C, where you have a weak type system that really doesn't do anything for you, or from Java, where you have a very strong type system where the computer does nothing to help you and you have to write out everything all the time and be very explicit, you will find that this is happily in the middle. You don't get as much type inference as you would get from Haskell, but you get something you can compile and execute, so that's a plus. My biggest issue with Haskell, other than not being able to read any of the code without the proofs, was that going from I have code on the screen to an executable is really hard. And so Rust is a much slower experience than, say, Go for compiling, but it compiles and it's pretty fast. It's good. So explicit mutability means that you have to say when you're going to be modifying some data and when you're not. And you actually express this through that type system. And that type system then gives you, is able to prove certain things and prevent certain bugs, which is awesome. You will hear a lot about these zero-cost abstractions, which is a great term because it sort of means zero cost. It means if you don't use it, it won't cost you anything. And if you do use it, it will not be any worse than what you would write. Hopefully better, because it's not better, yeah, it's better what I would write. Runtime independent concurrency safety. That's kind of a wordy one. So all of the checks happen at compile time, and then they get passed off to the actual back end. And once it gets to the back end, it doesn't look any different than the C that would have produced it, except that it's provably correct. A thing I love, errors are values. So we'll talk about option type and results and how there's no exceptions. And there's no null. Static automatic memory management is kind of the new way they're saying how there's no malloc, there's no free, it's handled for you. And you get concurrency without fear. There's no garbage collection. You get powerful macros. You have an actively good community. And off the bottom of the slide is, and as a bonus, you get a really cool build tool. So what does it look like? What does it look like? It is meant originally as a C-alike, so it inherits a lot of things from C, plus some ML. That's sort of where they have to match syntax, but a lot of things will look familiar to a C programmer. Bracing, you need a main function, you use C-style comments. It's a struct-based language rather than an object-based language. You use an ampersand to get a reference. You sometimes use a star to dereference. And they basically took a bunch of language research that was current, tossed it into a language, mixed it up a little bit, got rid of the things they didn't like, and let it cohese into something that would give them speed and safety in a concurrent system. Back to our original topics. So let's look at a little bit of code. Hello world. Now, who can read that, by the way? Yeah, I didn't think so. So again, I did change my themes, but they didn't export, so I super apologize because I really want to be going over the code. So I'm going to tell you what's on the screen anyways. So much like we talked about in the Python talk if you were there, so they spell subroutine FN. So you make a function Then you have your function declaration. Maybe if I just turned off all the color highlighting and redid it. All right, so here you have a main function, empty set of parentheses, which means it takes no parameters. Nothing after the parentheses means it doesn't have a return type. So like there's a lot going on even in the simple hello world. Bracing, because you're used to bracing. This thing that looks like a function, print line, takes some parentheses and a string. Print line is actually not a function. We're cheating there. That is a macro. Macros are really cool. I won't get to talk about them very much, but we'll use a few of them. Macros, you kind of need macros when you have a less dynamic language, because to do some of the things you need to do, you can't know what you're going to do to help the programmer. So like print line can take a string and interpolate into it and do a bunch of things, and you can't do all of that in a function because you don't know the type signature of what you're going to pass to print line. And so it figures it out at compile time and then writes that right code for you and to actually print it out to the world. But let's expand that one a little bit. At least you can read the comments, so that's kind of cool. With this particular color scheme, the next color scheme I went to, it was all black and you couldn't read the comments. So I hope this is better. So you get C-style comments, so double slash or multi-line with the slash star. So that'll help you when you're reading some code. The hash sign is not used for comments. It is used for directives, so a bit like your C preprocessor. And there are a lot of directives that you can see that are there to make the programmer's life easier. Again, it's a modern language, so it got to learn from older languages like us and Python. And so they've added doc strings. So if you use 3 slashes, that becomes a doc string. It's a bit like those triple quotes that we looked at yesterday in Python. So if you use 3 slashes above the function, whatever is next after the triple slash gets associated with that comment. And when you render the documentation, that will get marked down, formatted, and put into your documentation and made all pretty. And if there's examples in there, you can actually run them and make tests out of them and actually execute the comments in your documentation and find out whether or not they're actually still current, which is awesome. And if you don't like to put them in front, you can put them inside, and there's a slightly different / bang, which says go up instead of go down when you associate this. And then I explained that, yes, print line is actually a macro. You know it's a macro because macros end with a bang. Exclamation point. And the print line, that is probably a print macro. I never use that, but there's a print line macro, which includes the trailing new line. So it's say. And print line is awesome because it does interpolation. Nothing automatically, of course, but you're using the squiggly braces mustache style. So print line, a parenthesis you guys can't see, hello, squiggly braces, and then the right side gets interpolated in. You can do it by key value names. This is type checked, so you need the correct number of arguments to go into your string. And if not, that will fail at compile time. And the function signature gives you a whole bunch of stuff. It's all packed in there. It's very dense. They think it's a better form of documentation than it is, but it's really good, but it's not all the way to documentation. But it tells you many things. It tells you the visibility, whether or not this is a public or private function. It tells you the parameters. It tells you their data types. It tells you the trait constraints of those data types, which we'll get to later. It shows the mutability and the ownership and the interconnection between the input and output types, which introduces more words for the rest of the talk. So these two are actually equivalent. And there's a third equivalent form that is even more sugar as we get more and more down. So pub at the beginning says this is a public function and it will be exported. And if you don't say pub, it's not exported. And there's actually middle of the road, you can make this public to your modules but not the outside world. Then fn to define the function, then the function name, then optionally in less than, greater than, type information, right? This is where we start to look at it and we're like, oh, I didn't want to do types, what is going on? I've learned that I really like types. It's weird. Like, they're annoying until you start to see that, oh, I actually know the contract of what's happening on this function just from looking at this. So I would know in this case that these made-up traits of mine, that, and this is one of the things I would like to do in this talk is explain how to read it, because I find when I'm reading it, if I don't know how to verbalize it in my head, I just kind of glance over it. So this is a public function named foo that will involve two types, T and S. And type T must implement TT trait, which is a made-up word, and S must implement S trait as well as copy. And then we get to our parameters. The order is reversed from C, so it's the variable and then the type. So this function then takes a keyword of a parameter of input of type T and will output a type S. And then there's the function. They don't actually have a yada yada operator, so this actually would not compile because this function doesn't have anything that it returns, and it's supposed to return an S. You can also use the where format of this. So you say public function also foo on types T and S, input of type T returns type S, where T must implement T trait and S must implement both S trait and copy, and then the body of the function. And that is a bit to take in, so let's take a big breath. This was a lot to put out anyways. And when you look at documentation, which we won't get a chance to look at, but we could. When you go over to documentation, you will see all of this extracted automatically when you create the docs with the build tools. You get these beautiful HTML docs, takes those doc comments, takes your signatures, shows you the types and the structs. But when you look at the page, you see a whole bunch of this just over and over again, all the functions. Without the bodies. It's just boom, 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 all the signatures. And they're like, see, documented. And that can be overwhelming. It eventually makes sense. You will learn to read it. It takes a couple weeks. But that couple of weeks is not me. That is educational research of college students who were taking a course in Rust. So who knows? So static types. What does it mean to be a static type? It means it needs to be known completely at compile time. So you can't do your dynamic types and let me just, move this thing around. It was a string and let's stringify this number and change these types around. It all has to be explicit. It has to be trackable. Thankfully, the compiler does a lot of the work. So as you saw on the function signature, you do have to explicitly show all your types. You could make a type system that could infer some of those. That's what Haskell does. They found that even in Haskell, that it's best practice to declare all your types. So they decided they would, and that gives them a little more flexibility in other parts of the type system. So education is pretty cool. And what I mean by the compiler does much of the work is that you can declare your variables, and as long as it can figure out what that variable needs to be for the types to be correct, it will assign it that type. So specifically, like if you just put in a raw number and it needs to figure out if that's an int or a float, if you use it as a float, it can convert that from a raw, whereas a literal int can't be just converted implicitly to a literal float. You have to explicitly use a keyword to transition that. So yeah, what are the types? You get your basic primitive types: Boolean, character, float, and int. But you don't actually just get a float and an int. You get a 32-bit float and a 64-bit float. The Boolean is the Boolean type. The char is a character type. If you look closely, you'll see that is 4 bytes. So it is a Unicode thing. I'll get to those later. I would get to them later because they're in the notes on this, but it is in that 4-byte range that is valid Unicode, so the big range plus the other range. And so you can put raw Unicode in your variables, a character is denoted by a single character in single quotes that is representable in your terminal, then you can put it in your code. And you have signed types and unsigned types of each of the sizes from 8, 16, 32, 64, and 128. Those are all explicitly that size. And then you have iSize and usize, which are based on the platform you are compiling for. So if you're on a 32-bit platform, those will be 32 bits, 64, 64, 128. And also it comes up, that could be 16 or 8, because there's cross-compile targets down to embedded stuff, which is a really fun way to use Rust as well. A little tricky, because you don't necessarily get the whole standard library on an 8-bit microcontroller. So, and then as a primitive type, you just have a couple of compound types. You have the array and the tuple. We touched on those on Python yesterday. I wonder where they both inherited them from. But so a fixed size array is denoted with the hard braces of the type, semicolon, number, where n is the non-negative compile time constant size. So an array, you don't really use them very much because they're a fixed size. They exist statically. So if you know when you compile your code that you want an array of length 8 because you happen to know you have 8 things that you're going to stick in it, you can use an array. But if you want something that's actually going to be mutable and resizable, it's difficult. Actually, it is mutable, the array, you just can't make it a different length. Similarly, a tuple is a heterogeneous sequence that is made with the parentheses and the comma. So the types in your tuple don't have to match, the types in your array do. And tuples are used for passing lists of things, specifically back from the one return value that you have in your code. Related to those, you have slice, which is a dynamically sliced view into an array or other indexable system. So you use slices everywhere, or more likely a slice reference. We'll get to those. So if you have an array, you can borrow a slice of it, do some things with it, and then put it back. And a str is a slice of a string. And there's 2 string types. There's str and string, but str is really almost always a reference to str because that's a static string that is compiled into your code. So if you put a literal hello string into your code, you're going to have to turn that into a string type by stringifying it, which is getting into the weeds of the memory management. But you will get into those weeds, but by the time you're in the weeds, they'll feel like home. It's good. So back to our list in order, sort of, is we have explicit mutability. And we have a phone that will not keep the clock open. All right, we're about almost halfway through. So a few things going on this slide. So you don't get objects, you get structs. If you can channel back to when you were in C, right? A struct is just a list of things with types, and that struct is literally in memory, those things laid out one after another, and the compiler keeps track of those offsets, and when you try to get to one of them, it knows where to look inside that chunk of memory. And one of the constraints on you in Rust is that you must explicitly say when you're going to mutate something, so the compiler can keep track of what's going on. So this code would not work, almost works. So I create a struct called inner data, which contains a value, which is I32. That's how we read this. Then I create a struct definition for data. Now these are both capitalized, which is convention, and the opinionated formatter will tell you if you get that wrong. That contains an inner that's of that type, inner data. And so I can, in my function, I can create one of these with let. Think of it kind of like my. That's where you're creating your lexical variables here. So let d equal data. You can't quite, I'm sorry, you can't see these slides. Data, brace, inner data, val. So I'm not using a constructor, I'm just literally building one of these by saying I have a data that has an inner data that has the value 41. And now I'm gonna say d.inner.val, which is how I would get to something in a struct, use the dots, and I say I wanna set that to 42. And that would be an error. And it would look like this. And the errors are awesome. So I'm going to put a bunch of the errors in. So there you go. Not because my code was broken all night while I was writing. So cannot assign to field d.interval of immutable binding. Right? Okay, that's a decent error. But then it says, no, right here, hey, this binding is not mutable. So if you made d mutable, then I could assign to this. If you didn't want to make d mutable, then you're definitely doing something wrong here. I don't know which it is, but you got to fix that, because this will not compile. And so I can make this mutable. So I say declare let a new variable d that's mutable. And it will be mutable until I say it's not mutable. If I have it mutable, nobody else can have it. It's mine. So here we go. A simple counter implementation. This one is broken due to the same rules. So if I have a struct count, oh, it's really too bad. So what you can't see on the top line is a directive, which is the hashtag, hard brace, derive, debug, and clone. So I can say, hey, you know what, compiler? Imagine that I wrote the boilerplate code that would give me a debug version of this for printing. And so you put that there and it will write that code for you, because you don't need to write that code. This is the kind of stuff I love. Because later I'm going to print the counter value, and I'm going to use this special formatting type of : which says print me out the debug version. Now for that to work, your type has to support display or debug. One of the two is a trait. So instead of like creating that, yes, I get to traits in a second. So this would almost work. So I have a counter that has a mutable self inside of it, and I have a now function inside of it called increment that takes, I really wish you could read this. So I define a struct counter, like we did on the previous slide. Now I create an implementation for counter, which is spelled IMPL. And then inside of that, I create functions that will get a first, where my first element is self, which is the struct. So these become the methods on the struct. If you want to squint your eyes and pretend that it's an object a little bit. In this case, the first element is not just self, it is a mutable reference to self. Because as we'll get to in a second, in the everything is owned by someone, and you have to move those ownerships around to keep it happy. So we'll skip that one. Hey, it's not mutable. You fix it. You're happy. You execute the code on your slides, and you get count equals 1. Talked about zero cost abstractions. They are there. So like, if you are not using some of the abstractions for concurrency, they don't get compiled into your code. They don't affect your code. They are there. And if you want to use them, by using them, that gets put into your code automatically for you, and it will be at least as good as you would have written. It is probably better. So some people get really excited about the zero cost. They say everything's free. It's not really free. Although most of the costs are borne by you, the programmer, at compile time. So, because that's, for this part, for the runtime independent concurrency safety, which is to say, it does all of the checks statically and make sure that you cannot have a data race. Like, it's not that you can't ever do anything bad with memory, but you can never have a race condition of two things that are going to write to the same memory, and it's up to the random determinism of which thread went first. If you have code that looks like it's going to do that, it will not compile. And if it does compile, it will not do that. There's like a whole class of bugs that go away. Much like we got rid of, there's no null value, because null values there are errors everywhere. Speaking of errors, errors are values. This got me really hooked when I gave the talk on adventures in failure, how errors are handled in different languages. And we played with them a lot there. It's like, oh, do you use exceptions? Do you use classed exceptions, non-classed exceptions? What do you do? This is back on the no exception side of things. If you want to have an error, you need to return that to your caller. And you need to declare in your signature that you're going to do that. So there's no exceptions, there's no null. So what happens is if your function might not work, instead of returning a type T, you're going to return an option type T. which is either some value that worked or none to say it failed. And if you want to be more explicit about what your error was, you have a result type. And a question from the crowd. And please, questions are great. Yes?
What's the difference between null and none?
Ah, that is an interesting question. I actually know that one, so that's hot. The question from the crowd is, what is the difference between a null and a none? So null is a value. It's not a really useful, it's a value. None is a type. With the ownership system, null would, in addition to being a source of bugs and a pain, it would have to be owned by somebody. And if you were to return the null, you would have to declare the ownership of this null, even though it doesn't actually have any space anywhere in the computer. And it just doesn't work with the type system. And it's a hack to get around broken type systems anyways, so they got rid of it. But there's no value of null, but there is a type of none. And so options are of a type, and results, and you read this is a result of type T and error E. And so a result will either return a type or an error. And you have to get that and destructure it and see what you got back. So there's no like, oh, I forgot to check the return value of whether or not my file opened. Yeah, you can't do that. So, here's some examples. I actually wrote, so this is my safe division function. This is like a great example for options. So I take I32 for number and an I32 for denominator. And if the denominator is 0, I return a none. And otherwise, I divide them. And I divide them as floats. And I return sum, which is the type that is inside of an option to say that I have some value. And if I was to just try and print that out, in the debug type, I can tell that if I do safe division on it looks like 1 and 2, I get some value 0.5, and if I do it with a 0, I get a none. And there is an implicit return. Yes, that is a great point. So there is an implicit return from every statement. So in fact, there's a couple returns happening here. So in the if is a statement that has 2 branches. Each of those branches has a return value. So both of your branches have to return of the same type. These both do because that's a none and that's a sum, and those are both part of the option type. Then one second in the back, and then that value is returned sort of to the scope of what's happening inside the function, and since it's the last thing in the function, it is also returned. So sum declare, yes, that's great. Sum is the constructor for the sum type. So sum is a type. And so I wrap my actual value in a box that is of the sum type.
How does the sum type relate to option?
So an option is a compound type that returns either a none or a sum.
Okay.
Yes. There's a question in the back.
So you said that both the if and the else clauses have an implicit return. Does that mean that you cannot return from the function from within those, or?
You can. You can actually explicitly return with the return keyword at any point. They just all have to be of the same types. Excellent question. So right here, like that's not really what you would do of just printing it. It's how would you get that value out of the sum? And there's a couple ways to do it. So I like that about this language. There's always a couple ways to do stuff. So you can use an exhaustive pattern match with the match keyword. So match on thing, brace, patterns. So this one, if you could see all of it, would say match safe division of 1, 2, and then I have a brace, and I have 2 conditions. I have the none condition, and I say, hey, if I got a none, I want to print out a sad face. Whereas if I got a sum of variable x, and this declares a variable x and gives it the value, actually takes the value from inside the sum, and on the right side of the fat arrow, you now have an x that contains the value and owns the value that was in the option. So this is like the verbose explicit way. It's very nice, especially if you are definitely handling all of the two paths differently. So you can do a match. Some people don't like the match. So there's if let. So if let sum x equals safe division of whatever the division was. So this is read as if, so run safe division, get me that type back, and run a pattern match on it. And if the pattern matches this pattern, sum x, then continue having let an x equal the value that was inside that type. So it unboxes the type and takes your real value out of the option type. The else clause is not actually required here. So if it was a none, presumably you didn't want to do anything in that case, so you skipped it. Whereas in the match type, you do need both of these matches. It must be exhaustive. You can have a catch-all that says any other type, ignore it, or what have you. Because the option type has exactly two elements in it, it's like an enum, it's either going to be a none or a sum. This is guaranteed to match, and so the compiler checks that and says, hey, that's cool. You matched all of your types. If I hadn't included the match type, the none in my match type, it would be a compile error and say, hey, you didn't handle what happens here. Or you can use unwrap, which is sort of fun for when you're hacking, but you really, I give up my hands. So it says, do this and unwrap it. So if it's not a value, so if it's a value, pull it out, give it to me, I'll keep going. And if it's a none, explode. So you panic. Oh, is this an exception? No, you don't get to catch the panic. It just blows up. Because crashing is memory safe. Right? You're not going to corrupt the memory. You're not going to keep going. Yeah, I give up. They aim for a much higher bar than just crashing to maintain their memory safety. So you can say it's actually much more memory safe than other memory safe-ish languages. And there's a similar to unwrap is expect, where you give it a string so it panics with a custom message and says, hey, you divided by 0, I don't know what to do. And you crash and let the user figure it out. Whereas if you just did, I found this out while I was writing slides, if you just wrote 1 over 0, and I was like, maybe division already does this, right? I didn't want to look up the type, and I'm like, oh, right, it doesn't do that because I know it just gives me back an int. So what happens when you give it a 0? It panics. Although if it's a compile time panic, it will actually catch it at compile time and say, this code would panic. I won't let you compile it. Oh, I thought I had my error there. All right. And back into reading documentation, which again, hard on this background. When you look at the slides online, hopefully you'll be able to read them. Option type implements, among other things, and then. And so you can chain an option type. So you have a function that returns an option, and then you can dot and then another function inside of that, and that will return a new option. And you could do and then, and then, and then. And all of the happy cases would be handled. And if any of those became none, it would just short circuit through and be none at the end. So you can go read your Haskell monadic theory on why that's awesome. But it means that you can code to the happy case, and your nones just sort of exit early. And then if any of it was going to be a none, it's just going to be a none all the way through. But to read this, there's a public function named and then on types U and F that takes self, moves by moving, takes ownership of self, with one argument F, which is of type F, and it returns an option over type U, where F is Fn once of T. So where F is a function of T that returns an option of type U, and specifically it is a function that implements Fn once. There are 3 traits that your functions can have as to whether or not you can only run it once, or multiple times with a borrow. Or no, once, multiple times, or multiple times with mutability. We haven't even gotten to that part. This is like a week-long talk, so I'm going to give you what I can. That's an example of and then. Results are very similar. There's no nulls. Nulls are evil. That's actually just me from SQL. I hate nulls. Ownership, borrowing, lifetimes. These are the grand bargain you make with the Rust compiler. And you say, if I do this, you'll give me code that will be safe. It'll be memory safe. It'll be concurrently memory safe. And it will be concurrently memory safe even when you hand it off to the C compiler and turn it into machine code. It's amazing. But ownership, borrowing, lifetimes. So there's no malloc, there's no free. There's no free as in use after. There's no double free. So ownership, every piece of data is uniquely owned. So when you say let x equal 5, that 5 is owned by x. And then if you say, and that ownership can be passed. So let x equal 5, let y equal x. Well, y now equals 5. X is an invalid pointer that you can't use anymore. And if you try to use it, no, you can't use that. You lost it. It's not as scary as it seems. And then that ownership is destructed on the end of scope, and with it, whatever it owned. So it's like a ref counter that counts to 1. And the default ownership is move. So if you have a variable and you hand it to somebody, they say thank you, and it's theirs now. It's the book that you gave to someone. So if you call this code, it would work. I have this function called take and write to file that takes a file, and it does something cool. It prints to that file. It prints hello world to that file. Can't really read it, but the reason it's called take and write to file because that's telling you what it does. All these must be camel case, not snake case. No, wait, snake case, not camel case. Right, with the lowercase and the underscores. That's how you write a function. If I were to call take and write to file once, it would work. And if I tried to call it again, it would explode and say, you don't have file. Why are you trying to call me with file again? And it would happen at compile time. And you would actually get a pretty useful message that says, whoa, you tried to move a value you don't have at this point, that you moved at this previous point. Maybe you want to do something else. So the something else is you, instead of moving the data over there, you say, here, I'm gonna loan this to you. So here you can borrow my book. I can't read the book until you give it back to me. But it's implicitly given back to me or destroyed. That borrow is destroyed at the end of the function borrow and write to file, at which point my copy of file existed. So if, you can't do this, but if while that was running, I was back in this code and I tried to use file, I couldn't do that. So it would say, hey, whoa, you're trying to use file that you don't own. That's bad. But as soon as the function is done, I can do it again. So I can call this, and it's going to write twice to that line. And actually, it's an important enough one, and it's tricky enough that I wrote 2 different examples. I can't really decide which one I like more. Where am I at, by the way? Very late? Okay. Sweet. Oh, and I do have a question in the back. Yes?
So you said it goes whoa. Does it
Yeah.
go whoa at compile time or runtime?
It almost, the question is, when it goes whoa, does it do that at compile time or runtime? And the answer is almost always, in all cases, at compile time, if it possibly can. There's very few runtime panics. Obviously, there are some, because it doesn't know what you're going to do all the time with the input. But in this case, there would actually be, so had I tried to take this write and file, I would get a value used here after move compile error, and I could see it right then. And I'm compiling as I'm writing, and it's over here in the live checker, and it's like, whoa, that code's messed up. I'm translating for you. It doesn't really say whoa, which would be cool. Maybe we can recommend that to them. So this is another set of, oh, you can't read this off. So let x equal a vector of 1, 2, 3. So when you have a let, that introduces a variable binding, and it's that variable binding that owns the vector, right? the variable ending doesn't really exist outside of the compiler's mind space, but you have to keep it happy. And in these examples, you'll see you actually have to use a more complex type like a vector that if you just said let x equal 5 and then let y equal 5 or let y equal x, that'd be okay. Like primitive types implement copy, which means instead of having move semantics, when you move them somewhere, it just makes a copy because it's no more difficult to copy an int than to copy a reference to an int. So they're like, we just pass that over. So some of the super simple examples where you would just want to use some ints and pass them around are too simple, and it handles that for you. So, and yeah, that's ownership. So yeah, if you implement the copy trait, then when someone tries to move you, you get copied. Generally, that's only for primitive types, but you can put it on your type if you think your type makes more sense to copy. And then borrowing is how you get that temporary ownership, and that's done with the ampersand. Let's see. I really wish you could read these codes because they're really beautiful. Yeah.
But I think there's key things on those slides.
Yes.
It's impossible to read.
There are some key things on this slide. I'm trying to decide if any of them are important enough to read. So I'm like, I'm just going to skip these because they're impossible. I'm very upset with you. This teaches me to switch editors to Emacs to create my slides using, well, what I'll tell you about in a lightning talk later. But so if I said let x equal 5 and let y equal x, and I tried to print line an x, this would actually work because even though x and y both have ownership, because y would get its own copy of the 5, and it would have its own ownership. So this says let x equal 5, let y equal x, and then I try to print the value of x. Actually, well, this particular one wouldn't work because you can't see where I try to treat x as an array because this is a error on my slide. But I'm going to give a couple of these just to get a couple things. So here in your function signature, you can declare that you were taking a reference and which says, I don't need the actual thing, I need a borrow of the thing. Because otherwise, if I call a function with a value, then the value goes away to the function, and it could give it back to me explicitly at the end, but that would be a mess. So we've got borrowing where you say, here's the value, you can have it till the end of your function, then give it back. And you can even say, here's the value, you can have it to the end of the function, and you can modify it if you want to. Yes. I'm going to skip a couple of these because they're too messy for the comment. Yes. Lifetimes are something that is the third part of the memory model, wherein sometimes the borrow checker can't figure out how long things will last, and you have to tell it, hey, this is going to last at least as long as this. I know that because I'm maintaining them, and so it can figure out the lifetimes. It's getting better at lifetimes, but sometimes you do still have to say them, and if you want to declare something statically, there's a special static lifetime. Too complicated for the intro talk, but concurrency without fear, it will type check some concurrency things. Beautiful slide, you can't see. Wherein if you try to move a variable into your, I right down here, I'm going to spawn some threads, and I'm going to move my counter that we created earlier, and I'm going to let each thread play with it. And like this is something you might try and see, and then you would find out in GDB a while later that it was all broken. Whereas here, it would catch that and say, well, you're capturing a moved value, and you're trying to do it 3 times, and you can't do that. Yes?
If you do like Control A and select everything.
It might do. Yeah, let's try. Hey, let's write some code. Thank you. Ta-da.
I'm here all week, folks.
He's here all week. All right. Let's look at my broken concurrency one. This will be, I think, my last example because we're running a lot of time. So I've got my counter that I created earlier. I have it, hey, compiler, please derive debug and clone for this because that'll be helpful for me. So my struct is a counter that contains an internal variable count, which is an I64. So yeah, my counter just could be an alias type to I64, but this is good for slides. Then I've implemented for counter a function increment, which takes mutable reference to self and increments that internal counter. Right, so this is inherently not thread safe, right? I'm just like, hey, anybody who's got this, open it. And this would be a problem. This would compile, like the C equivalent of this would compile, and then it would break down the road. Whereas the type checker is smart enough that it will actually catch that type of error. So I'm like, hey, here's my mutable counter, and I'm going to spin up 5 threads, and each thread, I'm going to use move semantics to move whatever is on the stack here. Just move it all into the new thread, and so it will have a counter, and then increment it. And I'm going to have each of the 5 threads do that. And that will explode, and it will say, okay, you move this value into the closure right here. And then you tried to capture it over here. That was after it was moved. This is broken. And it also says, hey, it moved because your counter doesn't implement copy. So maybe you wanted to fix it by making that a copy, or maybe there was something else. And if you'd like to know more, you can try Rust C explain. E0382, so all the error messages have extended documentation about each of them, and they're probably localized and everything. And you can learn some more by trying this verbosely. It's like one of the few times you use Rust C directly instead of cargo. Where are those cargo slides? All right. And then I can make it slightly broken by using an RC, which is a ref counter. So this would work if I wasn't threaded and I was trying to modify it from multiple places. But it says, whoa, an RC is not thread safe because it's a little cheaper than an atomic reference collector. So you can't send that between threads. Like, oh, well, maybe I should try an arc then because it mentioned it right there. And so, right, you get in kind of low level into the weeds, you get very low level primitives. There are crates built on top of these, but arc, so make a new arc of a new mutex that controls access to my counter, and then put that in my threads, watch the threads finish, and then check the value, and hey, it runs, and it's awesome. And the last thing I did want to mention is cargo. So cargo is the build tool. It does all the things. Where's my other cargo slide? I totally missed the slide. So you can use it to create a library. You can use it to create your library, create some boilerplate code for you, to run your tests, to run your benchmarking, to format it, to lint it, to push it up to crates, which is the cpan-esque repository. And then there's plugins, so you can make it do more stuff. And if you were to look in a crate you downloaded, it will be exactly in a format that starts out like this. So at the top level, you have a cargo toml that says, hey, what's in this? Think of it as a config.yaml. And then you will have a literally named source directory, src. And then inside of that, you will have your code. And you will have either a main.rs or a lib.rs, depending on if you plan to build an executable or a library. So there's some opinionation happening. And that, I think, is well past my time, and I'm like a third of the way through my examples. So next time it will be even more smooth, because I will have written more Rust and read less Rust. But I will give, abstraction traits, no. Generics are awesome. So an awesome thing about it that Go doesn't have is generics. You don't have to write the same function 5 times, but you only have to write those functions because of types being tricky. That was going to be your quiz. No, I want to get to the you find more stuff slide. References. So there are a couple books that Rust makes in their documentation. The Rust by Example and the Rust book. These are both really excellent. I like that they come from slightly different directions, but they do both spend a bunch of the time in the same weeds I was, which was how does the borrow checker and immutability and references work. Then I just finished reading hands-on data structures and algorithms in Rust and hands-on concurrency in Rust, and these are both really wonderful. Unfortunately, at the end, and I was reading them concurrently, because, obviously. At the end, they both said, and what's a great book? That one. Which was true, but then I got to the end of my compile. And those are from Pact, and some of the other ones are a little more hit and miss that I've read. But these, both the writing, like the prose and the code, are both very readable and very welcoming. And the hands-on concurrency, I was like, sweet, that's going to be like what I got at like the Go level concurrency of like, here's how to write an app to like do some stuff. And it's like, no, like here's what's happening under the hood. Okay, we don't have a semaphore, but if we did, this is how you would write it. Here's what a mutex is, which means mutually exclusive. Nobody ever mentions that. Hello, that's what a mutex is, mutually exclusive. It's handled for you by the chip. A lot of great stuff in there. And again, that's me. And then, then there's the bonus slides, which obviously we're getting to. So I am totally excited to talk to you about some Rust later. Sleeping is good. But hit me up. It's really fun. I've been pairing with a friend of mine, and he's actually writing interesting things in Rust, so it's been really fun. I will actually like to pitch SQL Composer that Kenny is writing. Some of you know him from the Perl, and now he's doing Perl and Rust. And it's a beautiful type plus macros system so that you can take some SQL and keep track of like manually doing bind params, and it like does it all for you, and it's beautiful. So go check out SQL Compose. Thank you. Ooh. Rough cuts. So yes, I do apologize for my slides. They crashed it. I got a compile issue at 3 this morning. So they will be up on, that's not on this page. Where did that page go? They will be up on my blog, lowlevelmanager.com, which you can spell spaz.rocks, if that is easier.
Are you sure Mutex